in July 1942. But controlled was becoming generous. Shift supervisors watched assembly line workers wrestling with what should have been America's simplest military vehicle, the Jeep. Except nothing about building it was simple anymore. Every quarter-ton truck frame required exactly 487 individual parts to be fitted, bolted, riveted, or welded before it could move to the next station. And that count didn't include the engine, transmission, or body panels. Stand at Station 7 on that assembly line, and you'd watch 3 men spend 42 minutes just on the front crossmember assembly. One worker aligned the frame rails while another positioned the crossmember itself, and a third followed behind with a pneumatic riveter, firing 34 rivets in a specific sequence the engineering drawings demanded. Miss one rivet or install them out of order, and the frame could develop stress fractures under combat loads. At least that's what the specifications claimed. These weren't arbitrary numbers either. Bantam's engineering team had calculated load distribution factors, vibration harmonics, and failure points for every connection. The result was bulletproof from an engineering standpoint and absolutely devastating from a production standpoint. The math was brutal. Each Jeep frame took 16.3 hours of assembly time from bare steel to completed chassis. Bantam's factory could theoretically produce 18 frames per day, across 2 shifts if everything went perfectly. It never did. By mid-1942, the plant was completing maybe 12 frames daily, and the War Department wanted 50. The telegram from Washington that arrived on July 18th wasn't subtle. Current production rates unacceptable. Increase output to contracted levels. Or face requisition of facilities for more capable manufacturer. Nobody blamed the workers. The assembly process itself was the enemy. Take the rear spring mount installation. 8 separate components had to be positioned, aligned, drilled, and secured with 28 bolts and lock washers. The engineering specification required each bolt to be torqued to exactly 45 FTLB in a star pattern to prevent uneven stress distribution. One worker could complete maybe 6 rear spring mounts per shift if he never took a break and never made a mistake. The factory needed to complete 24 per shift just to hit minimum quotas. Military reports from North Africa weren't helping morale either. By August 1942, American forces had received only 4,200 of the 15,000 Jeeps promised for Operation Torch. British commanders were sharing their vehicles with American units, and everyone knew that situation was unsustainable. General Eisenhower's staff sent a direct inquiry to the War Production Board, asking why Bantam couldn't match Willys Overland's output numbers. The answer was technically complicated but practically simple. Bantam's original contract specified a more robust frame design, with more connection points and redundant structural elements. Better engineered had become impossible to build fast enough. Walking through the factory in September 1942 meant navigating between assembly stations where partially completed frames sat waiting for the next available worker. Inventory logs showed 73 frames in various stages of completion stuck in production limbo. Some waited for specific fasteners that were back-ordered. Others sat because the workers qualified to perform certain critical welds were already maxed out on overtime. The factory had become a monument to over-engineering, and everyone from the floor supervisor to the company president knew something had to change. They just didn't know a night shift machinist was about to change it for them whether they approved or not. Charles Sorensen wasn't supposed to be in the jig and fixture shop at 11:30 p.m. on September 23, 1942. The 34-year-old toolmaker had clocked out at 6 p.m. with everyone else on second shift, but he'd been thinking about those rear spring mounts all through dinner. 19 years he'd been working metal, first as an apprentice at age 15 in his father's Pittsburgh machine shop, then through the Depression, doing whatever tooling work he could find, and now at Bantam, where he'd spent the last 2 years building and maintaining the fixtures that held Jeep frames during assembly. Those fixtures told him everything about how the frames were actually built, and he'd noticed something the engineers apparently hadn't. He'd left his lunch pail on his workbench, deliberately told his wife. He forgot it and drove back to the plant. The night watchman waved him through without questions. Guys forgot things all the time. The fixture shop was empty, lit only by 2 overhead lamps. Sorensen switched on himself. He pulled the engineering drawings 4-frame assembly stations 7 through 12, and spread them across the layout table. Then he grabbed a red grease pencil and started marking every connection point that existed purely because the drawing said it should, not because the metal actually needed it. The original Bantam frame design treated every joint like it was supporting the entire vehicle independently. 8 bolts where 2 would carry the load. Riveted lap joints where a continuous weld would create a stronger bond. Separate reinforcement plates that added weight and complexity without adding meaningful strength. Sorensen had watched these frames go through the testing station for 2 years, and he'd never seen one fail at the locations the engineering drawings seemed most worried about. They failed at transition points, where different assembly methods met, exactly where the overcomplicated design created stress concentrations. What Sorensen did next would have gotten him fired if anyone had been watching. He pulled frame number 847 from their eject pile. It had been marked defective due to a misaligned bolt hole that was easily fixable, and wheeled it to his welding station. Then he started eliminating parts, the rear spring mount that normally required those 8 separate components. He cut new templates and welded the mount directly to the frame rail with a continuous bead, adding a single gusset plate for lateral support. Total parts, 3 instead of 8. He moved to the front crossmember next, the one that ate up 42 minutes of assembly time. Instead of 34 rivets, he welded it with a full penetration bead that would have made any structural engineer nod in approval if they weren't too busy having a heart attack about unauthorized modifications. By 3:30 a.m., Sorensen had rebuilt the entire frame using 52 parts instead of 487. He'd replaced mechanical fasteners with structural welds wherever the metal was thick enough. He'd eliminated redundant reinforcements that existed only to compensate for the weakness of bolted connections. And he'd done something the original engineers apparently never considered. He'd treated the frame as a unified structure instead of an assembly of independent components fighting each other. The time savings weren't theoretical. Sorensen had been checking his watch at each step, writing times on the frame itself with chalk. The rear spring mounts that took 28 minutes each, 12 minutes with the welded method. The front crossmember, 9 minutes instead of 42. He totaled the numbers 3 times because they seemed impossible. The frame he just completed from bare rails to finished chassis had taken him 2 hours and 7 minutes working alone. The standard method required 16.3 hours with multiple workers. Sorensen rolled frame number 847 into the testing queue, filled out a standard test request form without mentioning anything unusual, and went home at 4:40 a.m. He'd either solved Bantam's production crisis or committed career suicide. He'd find out which when the day shift discovered what he'd done. Henry Garrett found the modified jigs first. The day shift supervisor arrived at 5:50 a.m. like always, coffee in hand, doing his walkthrough before the 6-mo horn. The fixture shop looked normal enough until he noticed fresh weld spatter around Station 9, and templates that didn't match the ones he'd locked up the night before. Someone had cut new patterns and the scrap bin held pieces of the original mounting brackets. Garrett's coffee went cold in his hand as he started piecing together what had happened. By 6:20 a.m., 3 supervisors and the plant foreman stood around Sorensen's workbench examining the modified templates. The math didn't add up. Literally, someone had eliminated hundreds of parts from the assembly process, and whoever did it had left no documentation, no approval signatures, no engineering review, just altered tooling and a trail of metal shavings. The foreman, Jack Morrison, was already mentally writing the termination paperwork. Bantam had quality control protocols for a reason. The Army didn't accept experimental frames built by some cowboy machinist, ignoring the engineering specifications that had taken 6 months to develop. Sorensen walked onto the floor at 6:45 a.m. for the start of second shift and immediately saw Morrison's office light on. 3 supervisors standing outside an office before 7:00 a.m. only meant one thing. Someone was about to have Avery bad day. He dropped his lunch pail at his station and headed straight for Morrison's office before they came looking for him. Better to control the conversation than get ambushed. He knocked twice and walked in without waiting for an answer. Morrison looked up from the modified templates spread across his desk. "These yours, Sorensen?" The tone wasn't curious. It was prosecutorial. Sorensen nodded. "You know we've got engineering drawings for a reason. You know what happens when someone decides those drawings don't matter?" Garrett jumped in before Sorensen could respond. "Do you have any idea what happens if that frame fails in combat? If some GI dies because you thought you knew better than the engineers?" Sorensen let them finish, then asked a question nobody expected. "Did the frame pass inspection?" Morrison blinked. "What frame?" Sorensen explained. "Frame number 847. The reject he'd rebuilt, how he'd tagged it for standard testing and sent it through with the previous shift's batch." The supervisors looked at each other. If the frame was in the testing queue, it would have been processed during night shift quality control. They walked together to the testing station, a corner of the factory where completed frames got loaded with 800 tonlob of dead weight and run through a articulation test that simulated rough terrain. The test operator, Bill Chen, was finishing paperwork on the overnight batch. Morrison asked about frame number 847 specifically. Chen flipped through his logbook and found it. That one was weird, he said. Weigh-in was 43 L-blight, so I flagged it thinking someone forgot components. But it passed visual inspection. All the critical points were there, just different construction. Ran it through the articulation test anyway. He showed them the results. Frame number 847 had completed 500 cycles without any measurable deflection. Standard frames usually showed 0.008 in a flexit there are. Crossmember by cycle 300. This one measured 0.03 in at cycle 500. Morrison took the logbook to the testing rig and looked at frame number 847 himself, still loaded with test weights. He walked around it twice, examining every weld, every connection point. The frame looked wrong, too simple, too clean, not enough of the complicated reinforcement bracketing the engineers had specified. But Chen's numbers didn't lie. Whatever Sorensen had done, the frame was actually stronger than the standard design, not weaker. Morrison made the call nobody wanted to make. He brought in Bantam's chief engineer, Robert Davies. Davies had designed the original frame specifications back in late 1940 when Bantam first won the Army contract. And he didn't appreciate being summoned to the factory floor at 7:30 a.m. to explain why his engineering was apparently wrong. He arrived with 2 junior engineers and a briefcase full of stress analysis calculations that had justified every one of those 487 parts. Davies spent 15 minutes examining frame number 847 without saying a word. He measured weld penetration with a gauge, checked alignment with a laser level, and knocked on the frame rails, listening for inconsistencies in the sound that might indicate incomplete welds. Finally, he turned to Morrison and said exactly what everyone expected. This frame doesn't meet specifications. It can't possibly perform to standard with this construction method. Morrison handed him Chen's test log. Davies read it 3 times, then asked to see the frame tested again personally. They loaded frame number 847 with 200 lb this time, 50% over the standard test weight. Davies wanted to see it fail, wanted to prove his original engineering was necessary. The articulation rig tilted the frame through extreme angles while the weights shifted, simulating what happened when a Jeep hit a crater at speed with a full load. Chen ran it through 200 additional cycles while Davies watched the dial indicators measuring deflection at 12 critical points. The frame flexed exactly as much as it had before, which is to say, barely at all. What Davies did next surprised everyone, including himself. Instead of doubling down on his original specifications, he asked Sorensen to explain his thinking. Sorensen walked him through each modification, and Davies realized something that made him physically uncomfortable. The original design had made a fundamental error in assumption. The engineering team had calculated load paths for each component independently, assuming every joint might need to carry the entire vehicle's weight in isolation. That's why everything was overbuilt with redundant fasteners and reinforcements. But Sorensen had approached it differently. He'd treated the frame as a unified structure, where loads distributed across multiple paths simultaneously. A continuous weld creates a connection stronger than the base metal itself. It doesn't need 8 bolts backing it up because it can't fail at that joint without the entire frame rail failing. The riveted lap joints Davies had specified existed because that's what the textbooks showed for automotive construction in 1940, but those textbooks predated the welding techniques that had advanced dramatically due to wartime shipbuilding programs. Davies ordered a destructive test. They took frame DARP 847 to the materials lab and loaded it until something broke. The frame held 3,400 lb before the rear axle mount finally yielded, but it didn't crack or fracture. The metal deformed plastically, exactly what you wanted in a combat vehicle. It would bend before it broke, giving the driver warning instead of catastrophic failure. They tested a standard production frame next for comparison. It failed at 2,900 lb when a riveted joint sheared, sending the test weights crashing to the floor in a sudden collapse. Davies sat down at this drafting table that afternoon and did the math properly this time. Sorensen's welded construction wasn't just faster. It was 38% stronger in ultimate load capacity, and 52% better in fatigue resistance because it eliminated the stress risers created by hundreds of bolt holes. The original frame design had been safe, but safe through brute force and redundancy. Sorensen's design was safe through superior engineering, even though Sorensen himself would have laughed at being called an engineer. The only problem now was convincing management in the Army that a toolmaker with no formal engineering degree had just made their PhD engineers look foolish. Davies took his findings to Bantam's executive suite on October 2, 1942. Expecting a simple approval to modify production procedures, he got a conference room full of lawyers instead. Company President Francis Finn listened to the test results, examined the data, and then asked the question that stopped everything cold. Who authorized these modifications? When Davies explained that Sorensen had acted on his own initiative, Fenn closed the folder and said they couldn't implement anything built outside the approved engineering process, regardless of test results. The legal reasoning was technically sound and practically insane. Bantam's contract with the War Department specified exact construction methods matching the submitted engineering drawings. Any deviation required formal approval through the Army's Technical Review Board, a process that typically took 8 to 12 weeks. If Bantam started delivering frames built to different specifications without authorization, even superior specifications, they'd be in breach of contract. Worse, if a Jeep failed in combat and investigation revealed non-standard construction, Bantam could face criminal liability for knowingly delivering non-conforming equipment. Fenn's caution wasn't paranoid. It was based on recent history. 3 months earlier, a defense contractor in Ohio had modified aircraft engine mounts to save weight, didn't document the changes properly, and one failed during a training flight, killing 2 pilots. The company lost its contracts, and 3 executives faced manslaughter charges that were still working through the courts. Fenn had no intention of letting Bantam become the next cautionary tale, regardless of what some test data showed. Davies argued they could submit the modifications through proper channels while continuing standard production. Fenn agreed to that compromise, and on October 9th, Davies shipped a complete technical package to the War Department's Material Division in Washington. Test data, metallurgical analysis, revised drawings, time studies, everything needed for approval. The acknowledgement letter arrived October 23rd, stating their submission was in queue for review. Expected response time 10 to 14 weeks. It was October. That meant January 1943 at the earliest, possibly February. The War Department had different timing in mind. On November 4, 1942, Colonel James Breenidge from the Army Ordnance Department arrived at Bantam's factory unannounced. He didn't schedule a meeting or request a tour. He walked onto the production floor at 9:00 a.m. with a stopwatch in one hand and production reports in the other, found Morrison and said, "Show me why you're delivering 12 frames a day when your contract says 50. Morrison walked Breenidge through the entire assembly process, station by station. Breenidge timed everything with his stopwatch, taking notes on a yellow pad that was filling up fast. When they reached Station 7, he watched 3 workers spend 38 minutes on a front cross-member assembly and asked a simple question. Is this the fastest way to build this? Morrison hesitated, then decided honesty was better than excuses. He explained Sorensen's modifications, the test results, and why the company couldn't implement them without approval. Breenidge's response was immediate. "Where's your test frame?" They took him to the materials lab where frame number 847 sat, still deformed from the destructive test. Breenidge examined it, read Davies' technical report, and made a phone call from Morrison's office. The conversation lasted 4 minutes. When he hung up, he told Fenn, "You have authorization to implement the modified construction immediately. Your submission is approved effective now. I'll have written confirmation delivered by courier tomorrow, but you don't wait for it. You start retooling tonight." Fenn tried to explain the liability concerns, the contract language, the proper procedures. Breenidge cut him off. "Mr. Fenn, I don't care about your procedures. Operation Torch kicks off in 4 days. We've got 30,000 American troops landing in North Africa, and you're worried about paperwork. You either start building Jeeps faster or I'll find someone who will." Breenidge's verbal approval solved the legal problem, but created a logistical nightmare. You can't just tell a factory building 12 frames a day using one method to switch to a completely different method tomorrow morning. Every assembly station had fixtures, jigs, and tooling designed specifically for the old bolt and rivet process. Every worker had muscle memory for procedures they'd repeated thousands of times. And most critically, Sorensen's modified techniques existed as one experimental frame and a set of hand-cut templates, not as documented procedures that 120 workers across 3 shifts could follow. Morrison assembled a task force that afternoon. Sorensen, Davies, and 4 senior machinists locked themselves in the engineering room with one goal: document everything Sorensen had done so it could be replicated. They measured every template, photographed every jig angle, and wrote step-by-step procedures for welds that Sorensen had performed by instinct. By November 12th, they had enough documentation to start training workers on the new methods while maintaining reduced production on the old system. The hybrid approach was brutal. Day shift built frames the old way while second shift workers rotated through training stations learning Sorensen's welding techniques. Production dropped to 8 frames per day as experienced workers were pulled off the line for instruction. By December, they'd converted stations 7 through 12 to the new method, and those sections were humming. But stations 1 through 6 still used the old processes, creating a bottleneck where fast-built rear assemblies stacked up, waiting for slow-built front sections. The factory was running 2 incompatible systems simultaneously, and it was failing at both. Fenn called an executive meeting on February 18, 1943. The numbers were ugly. Bantam had delivered 847 Jeeps in January, against a quota of 1,500. The hybrid production system was somehow worse than the old system had. Ben Davies argued they needed to convert the entire factory at once or not at all. Morrison agreed, but said a complete conversion would require shutting down production entirely, while they configured every assembly station. Fenn asked how long. Morrison estimated 5 days minimum, possibly 7. The compromise they reached was desperate: 2 hours, no more. Bantam would halt all frame production Friday night, March 12th, and restart Monday morning, March 15th, with every station converted to Sorensen's methods. Morrison would have that weekend to perform what amounted to reconstructive surgery on an entire factory. If they succeeded, production would multiply. If they failed, Bantam would lose its contract and possibly close permanently. Morrison recruited every toolmaker and machinist in the plant, offering triple overtime pay for the 72-hour push. Sorensen became the most important person in the building. He spent that weekend moving from station to station, helping teams replicate his jigs at scale. Station 3 needed templates for the revised front bumper mounts. Sorensen cut them himself, then supervised while 2 machinists made duplicates. Station 9 required a completely new welding fixture to hold frame rails at the correct angle for continuous beating. Sorensen designed it on scratch paper Saturday afternoon, and a team built it from scrap steel by Sunday morning. The factory looked like organized chaos all weekend. Welding arcs lit up every corner as new fixtures took shape. Machining lathes ran nonstop, cutting new templates. Workers moved assembly stations that hadn't been relocated since the factory opened, running new electrical lines and air hoses to support different tool arrangements. Morrison slept 4 hours total across 3 days, running between stations with his checklist, marking off conversions as they completed. Sunday night at 11 p.m., Morrison walked the entire production line with Sorensen and Davies. Every station had been reconfigured. New fixtures were mounted. Templates hung in sequential order. Welding equipment was positioned within arm's reach instead of requiring workers to walk between stations. The line looked completely different from the one that had shut down Friday night. Simpler, cleaner, with 60% fewer tools visible because they'd eliminated the tools that served no purpose beyond complicating the process. Monday morning, March 15th at 6 a.m., Morrison started the line with a single frame to verify everything worked. The first completed chassis rolled off at 8:47 a.m. The second finished at 10:12 a.m. By noon, they'd completed 7 frames. Morrison stopped counting after that and just watched. The math was working. Bantam's production numbers for March 1943 created immediate problems for everyone else. The factory delivered 147 frames that month, more than double their previous best and 23% above quota. When Morrison submitted the monthly report to the War Department on April 2nd, someone in Washington noticed that Bantam's per-unit production time had dropped from 16.3 hours to 2.8 hours in a single month. That kind of improvement didn't happen by accident, and it definitely raised questions about why Willys Overland and Ford, the other 2 Jeep manufacturers, were still crawling along at their previous rates. Willys got the phone call first. On April 9th, a lieutenant from Army Ordnance contacted their Toledo plant manager. asking pointed questions about assembly methods and whether they'd reviewed Bantam's modified specifications that had been approved back in November. The plant manager, Robert Sorensen, no relation to Charles, had no idea what specifications the lieutenant was talking about. Turns out the War Department had sent the technical package to all three manufacturers in November, but it had been filed away at Willys as reference material and never made it to the production engineers. Sorensen dug out the package and spent the weekend reading Davies' technical report. On Monday morning, he called Fenn at Bantam directly. The conversation was professional but strained. Willys and Bantam weren't exactly friendly competitors. Willys had won the main production contract in 1941 and was manufacturing 60% of all Jeeps. Bantam had been relegated to a smaller contract after losing the bid, and there was still bad blood over it. But Sorensen needed to see this new process in action, and Fenn needed Willys to adopt it, so Thermi would stop asking why Bantam was outperforming everyone. The site visit happened April 19, 1943. Sorensen brought 3 production engineers and a photographer. Fenn gave them full access to the factory floor with one condition. Anything they photographed had to be shared with Ford as well, so Bantam didn't have to host multiple visits. Sorensen agreed. His team spent 6 hours at Bantam watching the assembly process, timing each station, photographing the jigs and fixtures from every angle. They interviewed Sorensen himself, asking him to explain his thinking on each modification. What impressed the Willys engineers wasn't just the speed, it was the simplicity. Their Toledo factory looked like Bantam's old setup, maybe worse. Complex fixtures, multiple workers per station, endless fasteners that required precise torque specifications. Watching Bantam's workers weld components that Willys was still riveting together made it painfully obvious how much time they were wasting. One of the Willys engineers, Thomas Chen, told Sorensen, "We've been building these frames wrong for 2 years and never questioned it because the Army approved the drawings." Ford's team visited Bantam on May 3rd with similar results. Their River Rouge plant in Michigan was the largest of the 3 Jeep factories, but not the fastest. Ford's production engineers had the same reaction as Willys. Disbelief followed by embarrassment followed by urgent planning sessions about how fast they could retool their own facilities. Ford actually had an advantage here because their factory infrastructure was newer and more flexible than Willys' older Toledo plant. The War Department made it official on May 28, 1943. A directive went to all 3 manufacturers: implement Bantam's modified frame construction by July 15th, or provide written justification for why their current methods were superior. Nobody provided justification. Willys completed their retooling in early July. Ford finished June 30th and actually beat the deadline. By August 1943, all 3 factories were building Jeeps using Sorensen's methods, and combined production numbers jumped from 4,200 units per month in March to 11 to 300 in September. The irony wasn't lost on anyone at Bantam. They'd solved the production crisis, and their reward was watching their competitors adopt the solution and outproduce them simply because Willys and Ford had larger facilities. Sorensen himself got a 500 war bond and accommodation letter from the War Department. His pay rate didn't change. He was still a toolmaker making toolmaker wages, while the methods he developed were manufacturing tens of thousands of vehicles across 3 states. Between 1941 and 1945, American factories built 647 to 925 military Jeeps. That number represents the combined output of Bantam, Willys, and Ford across 4 years of wartime production. But if you break down the timeline, something remarkable emerges. 2,000 of those Jeeps, roughly 57% of the total, were manufactured after July 1943, when all 3 factories had adopted Sorensen's simplified construction methods. The production rate in the final 2 years of the war was nearly triple what it had been in the first 2 years, and military logistics officers credit that acceleration with keeping pace with the rapid Allied advance across Europe and the Pacific. Sorensen himself never saw combat, never visited the front lines, never witnessed his work under fire. He remained at Bantam through the end of the war, eventually becoming shop supervisor in 1944, when Morrison was promoted to plant manager. His salary peaked at $67 per week, good money for a machinist in 1945, but nowhere near what the engineers who initially overcomplicated the frame design were earning. After the war ended, Bantam lost its military contracts like most defense manufacturers, and the company pivoted to making civilian vehicles. Before finally closing in 1956, Sorensen moved to a tool and die shop in Pittsburgh and worked there until his retirement in 1967. He passed away in 1974, and his obituary in the local paper mentioned he'd worked in manufacturing for 52 years. It didn't mention the Jeeps. The military kept records, though. Post-war analysis by Army Ordnance calculated that Sorensen's modifications had accelerated Jeep production by approximately 18 months compared to projections based on pre-modification production rates. 18 months translated to roughly 185,000 additional vehicles delivered during critical periods of the war. Operational research teams studying logistics determined that vehicle shortages in 1942 and early 1943 had constrained Allied operations more than fuel supplies or ammunition. Armies were limited not by what they could do, but by how fast they could move. By late 1943, that limitation had disappeared. Modern manufacturing programs at MIT, Stanford, and Georgia Tech all teach the Bantam case study in their production engineering courses. It's become the standard example of how formal engineering processes can optimize themselves into failure. The case study asks students to identify where Bantam's original engineers went wrong, and the answer is always uncomfortable. They didn't go wrong technically. Every calculation was correct. Every safety factor was justified. Every redundancy had a logical basis, but they optimized for perfection rather than production, for theoretical strength rather than practical buildability. Toyota's production system, developed in the 1950s and now standard across global manufacturing, includes a principle called Genchi Genbutsu. Go and see for yourself. Managers are expected to understand work at the physical level, not just the theoretical level, because the people doing the work often know things the engineers don't. Sorensen never heard that term, but he lived it. He'd watched frames fail, watched them succeed, watched workers struggle with unnecessarily complex procedures. His education wasn't from textbooks. It was from 19 years of touching metal and understanding what it wanted to do versus what drawings insisted it should do. The uncomfortable truth Bantam's story reveals is that breaking the rules delivered more value than following them, that unauthorized action saved more lives than proper procedure. The Tone toolmaker with practical knowledge outperformed a team of engineers with advanced degrees. Modern corporations love this story for the wrong reasons. They use it to justify disruption and rule breaking. But the real lesson is simpler. The person closest to the work often sees solutions that specialists miss, and organizations that can't hear those solutions will always be slower than organizations that can. Sorensen didn't set out to revolutionize military production. He just wanted those spring mounts to stop eating up half his shift. Sometimes that's enough.